Hi, this is Rishabh Bandyopadhyay, and I'll be presenting our work, SketchINR, a first look into sketches as implicit neural representations. So I'll be starting off with what vector sketches are and how they are represented on a 2D canvas. A vector sketch is a sequence of coordinates traced by an artist over a digital canvas. By retracing these coordinates one by one, we can obtain the raster, that is pixel equivalent, of the corresponding vector sketch. Popularly, vector sketches have been represented autoregressively, as they can be encoded as a sequence of coordinates and decoded one coordinate at a time. We challenge this form of representation as it is inherently slow, only one coordinate can be decoded at a time, and it does not allow for high-fidelity reconstruction, specifically for long sketch sequences. We make an attempt towards representing vector sketches as neural implicits. For this, we start by thinking of sketch as a function of time. At each timestamp, each coordinate of the sketch is drawn, thus creating the entire sketch from progressive timestamp. We put all of this as an implicit function so that we have x, y, delta as a stroke coordinates and pen state as a function of time parameterized by theta. Now for each timestamp t, we have the corresponding pen states and coordinates, allowing us to reconstruct the entire sketch by sampling different timestamps. We add to this idea by representing sketch as a function of both time and stroke. For each timestamp and for each stroke stamp, we retrieve a coordinate corresponding to the sketch. This gives us explicit control over the number of strokes and the resolution of each individual stroke. The direct benefit of using this form of representation is that we no longer have to depend on previous sketch coordinates to predict new points. What this means is that we can parallelize. By querying multiple timestamps at once, we can generate the entire sketch in one pass instead of one coordinate at a time. With parallelization, we obtain as much as 100 times speed up over previous autoregressive forms of representation. Our network consists of MLPs, where for each timestamp and stroke stamp, we get the corresponding sketch coordinates. A combination of MSE loss from the vector sketch and visual loss from the raster sketch are used to optimize the network. We demonstrate high-fidelity reconstruction, where the output matches the ground truth very closely, even for complex sketches like that of a scene. We find that autoregressive models like SketchRNN cannot keep up with reconstruction quality even at lower complexity sketches. Since we can reconstruct the sketch with high fidelity, we can only store the sketch latent as a compressed form of the vector sketch. We find that storing the sketch latent yields better quality sketch reconstruction and occupies lower space than other sketch compression algorithms. We demonstrate additional potential applications of our work, including use for generative modeling of sketches. For this, we encode sketches, mapping them to a VAE-like latent space from which we can sample later for generating new sketches. As an application of generative modeling, we demonstrate sketch completion, where we optimize the implicit latent code to fit a partial sketch. This allows us to perform sketch completion as good as autoregressive models, but faster. Here is a qualitative comparison of sketch completion performed by our network and by autoregressive SketchRNN. As discussed earlier, we can perform sketch generation by generating new implicit latent codes that can be decoded by our model into corresponding vector sketches. We can also perform vectorization of raster sketches by encoding raster sketches into latent codes, which can be decoded into their vector forms. We can also perform abstraction control. By adjusting the number of timestamps we use for sampling the final sketch, we can adjust to some degree how abstract or detailed the resulting sketch is. In the bottom figure, we can see that detail increases from right to left and abstraction increases from left to right as we reduce the number of timestamps we sample. More details of our work, including qualitative and quantitative analysis with previous works, are there in the paper. We have released our source code, which you can find in the project page. Thank you.